Very good. So now let's start with the next topic, that is how to apply these optimization algorithms to the optimization of neural networks, which are now, you have a course on neural networks right now, do you? Okay. So neural networks now have revolutionized many data processing and data analysis. So we will start introducing neural networks. I know you know it, but it's still, it has to have common comprehension, mainly. And then we will, most of the work that is done with the neural networks is this gradient descent. And gradient descent in neural networks, it is called backpropagation. And then we will see a few more algorithms that are related. There are variants of gradient descent. Naturally, we already know them, but we will see how they are used in neural networks. Okay, so a neural network is nothing more than this. So they are very basic operations that originally they try to mimic the behavior of a neuron. So a neuron has some dendrites that receive the input from other neurons, so from the previous neurons in the network, and then they somehow combine all this information into a signal within this cell body, and then this combined signal is transferred to the next neuron through the axons. So in a way to try to mimic that, so let's say that we have a number of inputs. So we combine them, and the combination is a linear combination of the input signals, and then we go through a non-linear function that somehow simulates how this combined signal is transformed into the output. So mathematically, it is like this. So you have some signals x1, x2, and let's xn. Then you multiply by some weights. So the neuron, not all the neurons of the same output x1 that is connected to one neuron and to another neuron. So each one of the receiving neurons give different weights to that signal. And then there is a bias. So this bias here, it is modeled with that is some bias. Let's say that W0, W1, W2 represent different input signals, and the bias is not represented here. Sometimes it is. And then this is a linear combination. You go through a non-linear function, and then that is the output of your neuron. And what turned out is that this way of calculating, when you combine them one after the other, you can model almost any function. So if you give me observations, pairs of observations, so if you give me a set of observations, x, I, y, I, and these can also be vectors, then, and you give me many of these, I equal I to n, then I can always find a function that approximates these observations in with as much accuracy as I like. And the parameters of that function are this theta, that are the weights of the neural network. And I can minimize the distance between the observations. Let's call it 1 minus n of theta x squared. So these are two matrices that collect all this information. So I can minimize this error as much as I like up to the level of noise, so that my function my neural network is able to reproduce the outputs that you're getting. Okay, so and they are universal approximators under some relatively mild conditions. So you can approximate any function as long as it is smooth enough. So what we have presented here is just a neuron, a single neuron, but then a neural network is a collection of neurons that are organized into the so-called layers. So you have a layer of neurons that is going into another layer of neurons and another layer of neurons, and then you have to find the weights of all versus, because these neurons are connected all with all. So this architecture is called a dense layer, and that there are many different kind of architectures, but this was the first one. And then one of the keys to find the weights is that we have now new algorithms. So we have the standard gradient descent. So standard gradient descent, here you have millions of data points. So these XY pairs, you have millions of those. And then you don't want to compute the gradient with all those, so you do it in small batches. So we have a version here, batch gradient descent. And then if the batch, let's say it has 10,000 points, then you go relatively smoothly to the minimum. So this is this whole function that I brought here. So this is called the loss function. So what we are having there is, in this plane we have the weights. Okay. So you have the weights on the theta parameters, they are the same. And here what you have is the loss. And then there is a landscape here. It is a 3D landscape. Well, not 3D. It is many more dimensions because you have many weights. That's somehow we are represented it in 3D. So here are the weights. There must be a minimum of the loss function for some combination of the weights. So the gradient descent, if the batch size is big enough, you would go relatively smoothly. But let's say that you do mini batches. So instead of having thousands of elements of data points in the batch, you have just 8, 16 points. Then each one of the updates, because the input data is noisy, then your gradient is also noisy. And then you would go making these zigzags. And it can be even worse. So you can do this stochastic gradient descent that is even more random. But the key here is that you can go, in general, the trajectory goes towards the minimum. So even if the single step is noisy, the general trajectory goes towards the right place. And here is another kind of representation of the same thing. So here are the local minima, and then how you go from a point that would be your initial weights to the global minimum, hopefully. You know that all these gradient descent algorithms, they are not going to go to the global minimum. And because now you understand this state, this function is nonlinear in theta. So nonlinear in theta means non-convexity. So it is a non-convex problem. And non-convex implies many local minima. So this is one of the big problems of neural networks, that training them, it is somehow very tricky. But we have now these stochastic gradient descent algorithms that help quite a lot to escape from local minima and go into the right direction. The key is that, so what is stochastic is that this minimization, these matrices that we used here, so in principle, they should take all the values, But in practice, what they do is that they take a random subset of those values. So let's say that here you have million points. So these ones only contain 8 points. And these 8 points are different. So if you think of the loss function, the loss function is changing all the time because it depends on which 8 points you chose. So the goal function is changing all the time, but the global minimum is the same for all of them. So hopefully you will, in each step, you converge to a local minimum, but hopefully, because it is changing so much, you will go to the global minimum. Okay, so why deep learning has started in the recent years and was not like 30 years ago. So the reason is that because the word deep means you have many, many layers. So there are architectures with hundreds of layers there. So hundreds of layers means several billions of parameters. So if you have to train several billions of parameters, you will need many training examples, really, really many. And for that you need big data. And now we have many domains in which you have such a big amount of data. The other ones, and this has been also very important, is that you have to do a lot of calculations. All these calculations can be done in parallel because each one of the columns of these matrices can be processed independently. So we have now the GPUs. The GPUs, you know what a GPU is? Yeah, all of you? Okay, so now we have the GPUs, and these GPUs allow these massively parallel calculations. And you don't access the GPU directly, but you do it through libraries. And the libraries, typically they were TensorFlow and Keras and PyTorch. And now there is a new one, JAX, that is also is even faster and simpler to use than these ones. And this stochastic optimization that we have seen during the course has been really, really important. And then the changes in the network architecture. So this architecture is the most simple one, but you can have a lot of combinations that I will not enter because that is more for the course of neural networks. But that has been a lot of changes and advances in these network architectures. Okay, so now let's concentrate in the part that we are concerned, that is the optimization part. So how to find the weights. We will show it through a very simple example. So let's consider this neuron. So this neuron has a number of inputs, and then you have the weights, and then you have the bias, and then you combine all of that in a linear way, and you go through a nonlinear function that we will call G. And then the output is this nonlinear function is also called the activation function. So it is the activation applied to this linear combination. And very typical activation functions are this one. So the ReLU is one of the most famous today. So let's say that you have the identity function, that is this line. So it is identity times a step function. The step function is defined in this way. Then the leaky ReLU. The leaky ReLU is like, the problem with the ReLU is that if your combination is negative, if the combination is negative, then there is no, if you change the weights, there is no change in the output. And now you know, because you know gradient descent, so that means that the gradient is zero. And if the gradient is zero, I don't have a clue how to change the weights so that I can get a better loss function. So why don't we make it not zero, relatively small, so with some loss function that is, or some activation that somehow it is proportional to how negative you are. So this is this leaky revenue. So it is the revenue plus the leaky part. The leaky part is, okay, I will not let the whole combination go through, but just a fraction of it. And it is defined in this way. Then you have the logistic function. That the logistic is not, it is shown here, the green one. Then you have GELU. GELU is somehow a combination of these two ideas. So it is X and then the CDF. So it looks like the revenue, but in the negative part, that is a little bit more information than the leaky revenue up to some point, so up to here, and then the gradient goes to 0. Okay, so let's analyze how the neural network transfers the information through the network. So let's say that you have a couple of input neurons. So these input neurons go through some weights, then they are combined into this layer, and the combination is this one. So it is the activation. So in general, so let's continue. So we do the combination. The combination is this that we will call set, and then set goes through the activation function, and you have the activated output. So you have the activation from the previous layer. You go through the weights plus the values, and these are vectors. So this the whole thing is a vector. Then this vector goes through the activation function, and you have the output for the next layer, and then start again. Okay, so non-linearity is necessary to have this property of universal representation. So let's follow the path with a non-linear function in between, and then we will repeat it without the linear function, without the non-linear function. Okay, so you have an input, then you go through the first layer of weights, then you add the bias, and this is our linear combination that we will call set 1. So set because of the linear combination, and 1 because it is in the first layer. And then you go through the non-linear function, and then you have the activation layer of layer 1. And then this activation layer goes through the weights. So the X here are the input to the layer. So the input to the layer is this A1. And then it goes through the weights, the bias, and then the non-linear function. And because we only have 2 layers, that is our output. Okay, so let's compose all that. So we start from the beginning. So this is our input, then we go through the first weight combination, then the non-linear function, and then this is the input for the next one that multiplies by the second layer of weights plus the bias and the output. Okay, so you see that this information progressing is nothing more than function composition. So you are composing different functions and in a non-linear way, because the sigma function is non-linear. Okay, so let's say that you draw the non-linearity from it. So the input goes through the weights, and then you have the linear combination, the input, and then you don't have a non-linear function, and then you have a second layer of weights, and that is your output. So if you now compose everything, so you have the first linear combination times the second matrix of weights plus the bias. So you expand all that, you have this thing, but then what you have is X multiplied by a matrix and then some vector. So it is equivalent to this. So if you don't have the non-linearity in between, all you have is just a linear combination of the input layers. And a linear combination is just an input layer. So an hyperplane, for instance, in R2, it is a line. In R3, it is a plane. So in general, it is a variety that has n minus 1 dimensions than the dimension of your input vectors. So those are pretty simple shapes. And the nonlinearity, what allows you is to, instead of having lines or planes, to have curves of any arbitrary shape. Okay, very good. So nonlinearity is crucial to have neural networks. Okay, so now let's go for the optimization of these weights. Okay, so that you will have a cost function. So let's say that the cost function, by the way, this is I have taken all these pictures from this web page. So you have a cost function that is the activation layer of your last layer in the network minus the desired input. And then a very typical loss function is squared. Okay, and it is not the only one, but it is very simple to track and do manually. So let's do it with squares. Then you will update your weights in this way. So the weights at the given layer will be the current weights at that layer minus some learning rate and then the derivative of the cost function with respect to the weights of that layer. So this is just gradient descent. Yes, that's it. We already know that pretty well. So what we know we are doing is somehow in a schematic way. So you have a cost function as a function of the weights, and because it is a square, you have square shape, parabolic shape. And you know that this is a simplification because the problem is non-convex, and then you would have many local minima. Okay, so you start from some initial weight. Then you approximate the function C, so the red one, by a linear variety that is defined by the gradient. And then you advance a little bit in the direction of the gradient. And this how much you advance is given by the learning rate. And then you go to here, and then you start the process again. So you approximate by the new gradient, and then you iterate. So until you find a local minimum. Okay, so it seems that we have to compute the derivative of the cost with respect to the weights. So let's look at 3 layers. So we have to compute the cost with respect to the weights of the layer 3. So it is the cost with respect to the activation. That is the last operation we did. Then the activation with respect to the linear combination, and then the linear combination with respect to the weights. So this is just a chain we will apply to the differentiation. And then the cost with respect to the weights of the second layer. So it is up to here. It is the same that we had before. So we had cost with respect to activation of the third layer, activation of the third layer with respect to the combination of the third. So these first 2 terms are the same as these ones. And this structure is exploited to compute efficiently the derivatives. And from this point, they diverge. So here we compute the derivative of the combination with respect to the weights, but here it is the combination with respect to the activation of the previous layer, and then activation of the second with respect to the combination of the second, and then combination of the second with respect to the weights of the second. And for the first one, these 2 terms are already these ones. These 2 terms are these 2 terms that we have there, and then we have the same extraction as in every layer. So in every layer, you see that what we add is the derivative of the combination in that layer with respect to the activation, activation with respect to the combination, combination with respect to the weights. So here it is the same. Okay, so it is all the time the same, and the terms that go in front of that are terms that already appear in the previous calculation. So somehow these libraries that we discussed before, these libraries here, somehow keep track of all these terms that are needed for doing the backpropagation. Okay, then let's take a very simple network like this one, and let's follow forward the propagation. So the information from the input to the output. So you take this input and you have to compute the output of this network, of this neuron. So the output will be you multiply the two inputs by the two weights, and then go through the nonlinear function. And the same for the second one, the same for the third one. Okay, these two are in different colors because they have already been calculated. Okay, and then now you have all the outputs of the first layer. And this is what can be done in parallel, because each neuron, the calculation of each one of the neurons is independent from the other neurons. And then that is why the GPUs are important. So you have calculated the first layer. Now you can compute the second layer. So the second layer will be the weights of the previous layer. So the weights here between layers 1 and 2, and the outputs of layer 1. And then you go through the nonlinear function 4, and then the nonlinear function 5. So now you have the output at the second layer. Now you compute the same for the last layer, and that will be your prediction. So your prediction is the output of this layer, and you can compare the desired value. The desired value here is called Z, and you can compare it to your prediction. Your prediction is Y. So there will be a difference, and that difference is called delta. Okay, so now the question is, okay, if this delta is not zero, if delta is zero, I don't have to do anything. I have perfect prediction. I don't touch the weights. But if my delta is not zero, then how do I update the weights such that next time my delta is smaller? So somehow we have to transfer that to the previous layer. So you have seen this delta. So now you try to attribute how much of this delta is coming from this branch and how much of this delta is coming from this branch. And you will call that delta 4 and delta 5. Here in the drawing, because I have taken it from some web page, in that web page they say it is like this, but in practice, in reality, the derivative of the nonlinear function should be taken into account. So probably it is just not to clutter too much the drawing, but mathematically it is not totally correct. It has the right idea. So the right idea is how much of this delta, how much of this second is coming from this branch, how much is coming from the other branch. And then from this delta, I now compute two other deltas. So delta 4 and delta 5. And then I do the same. How much is coming from this branch? How much is coming from each one of the branches? And that, so for instance, this delta 4, part of it is coming from this neuron, but in delta 5, there is also a part that is coming from that neuron. So this delta, we call it delta 1. So delta 1 has a contribution from these two deltas. And the same for all the other neurons. And then you keep propagating back the error from the output to the input, so that you can try to attribute how much is coming from each one of the neurons. And now it is where you have to update your weights. Somehow here the expression is correct. So we will compute a new weight, and this new weight is the current weight plus learning rate times the delta that we have collected from the backpropagation times the derivative of the function times x1, that is the input to that neuron. And you apply the same in all the neurons. So if you look at all the expressions, they are all exactly the same. So let's say that I want to update each one of these weights. So these weights are affected by this delta 4 and the derivative of f4 at that point times the input. The input is here it was y1, y2, y3, so you have to update it. Okay, so if you want a more detailed explanation of the backpropagation in a mathematical way, here it is a very good explanation. And then let's try to do that tracking of the weights and the updates. Let's do it manually. Before doing that, just a note. So because we are in gradient descent, even if it is for a batch, so in the batch, what you compute is this. In this Q is the loss function. So you are computing the derivative of the loss function with respect to the weights, and then you are updating it with some delta weight. So if this loss function, the derivative of it is 0, and it is 0 in different ways. So one way is that it is a local minimum. The other one is that region is not exactly 0, but it is very flat. And it is very flat for a period of time, so for a period of weights. So if that derivative is approximately 0, that means that you will be updating your weights very little. So you will not learn much in regions where the derivative is 0. So that is why sometimes these leaky ReLUs or JLUs, they are preferred over ReLUs. Because for the ReLU, if you are in this area, there is no change. You change the weight, but there is no change in the output. So the gradient is 0. And then you don't change your weight anymore. Okay, so let's collect all the formulas that we have and let's put some names to remember. So the derivatives of the cost function with respect to the activations, we will call them E. So there, let's say that we have just 2 layers, just to keep easy track of everything. So the derivative of the cost with respect to the second activation layer. So the activation vector of the second layer is E2, and E1 will be the derivative of the cost with respect to the activation vector in the first layer. And because of the rule chain, we have the chain rule, sorry. So we have that the cost, so the cost with respect to the activation is cost with respect to activation of the second, activation of the second with respect to the combination of the second, combination of the second with respect to the activation of the first one. And then let's call delta the derivatives of the cost with respect to sec. So it is derivative of cost with respect to activation, and then activation with respect to the combination. And here it is again the chain rule, but now a little bit longer. We have to go one layer more. So it is cost with respect to activation of the second, activation of the second with respect to the combination of the second, combination of the second with respect to the activation of the first, activation of the first with respect to combination of the first one. Okay, now, so now we have names for all these derivatives. Now let's look at how the activation transfers into the combination of the next one. So it is through the weights and the bytes. And if we compute the derivative of the combination of the cost with respect to the weights, because here we want the derivative with respect to the weights. So with respect to the weights of a given layer, it is derivative of the cost with respect to Z, but that we have, that is delta, and then derivative of Z with respect to W, to the weights. And now here we saw at the very beginning of the course these matrix calculus formulas of how to differentiate the expression with respect to a vector or with respect to a matrix. So here it is with respect to a matrix, so the derivative is just this one. Somehow it looks familiar because what we have is a variable times from the point of view of the derivative, this is a constant, so it is just a constant. Very good. So now let's put some numerical examples so that we can track all these calculations. So let's say that we have at a particular moment, we have these two weights, 0.5 minus 0.5, and we have these two inputs, 1 and 0. So they go through the linear combination, and the linear combination is this one, so it is 0.5 times 1 minus 0.5 times 0, that is 0.5. Now let's say that our activation function here, to have something easy, is ReLU. Okay, so this is the linear combination. Now ReLU of 0.5 is also 0.5. So now we have the activation here. We go to the next layer. Let's keep it very, very simple. So let's say that we have a single neuron at the output. So we have a single weight, and that weight at the moment it is 1. So now the linear combination at this point will be the 1 times the 0.5. That is the activation of the previous layer. And that gives us 0.5. And now we go through the nonlinear function of the output layer. And let's say that that function is this one. It is the logistic function. So sigma, that is this one, applied to 0.5 is 0.62. And this is our output. Our desired output is 1. So it is not that far from 1, but it is not 1. So how can we change the weight such that this gets a little bit closer to 1? Okay, then we can compute the cost function. So the cost function, let's say it is this Euclidean distance. So it is the desired output 1 minus our current output is this one, 0.62. The 2 on top is not a square, it is just the second layer. So it is this, so 1 minus 0.62 squared divided by 2, that is 0.07. Okay, good. So now this is the forward pass. Now let's do the backward pass. So for the backward pass, so all these will stay the same in the next slides. And by the way, I wrote here y prime with respect to x. So y prime is this thing, and this thing with this definition of y, it is y times 1 minus y. Okay, good. So this part will stay, and this is the one that will change. So now we have to compute the derivative of the cost with respect to the output. So with respect to the output, so it is, so we have 1/2 of this thing squared. So it will be 1/2 times 2 times this term, and then the 2 times with the 1/2 cancels. So we have this term times the derivative of this with respect to x1 to x1 2, the 2 because of the layer, and this derivative is minus. It's minus 1. So all this thing is minus 0.378. Okay, so now we have the derivative of the coast with respect to the activation of the last layer, that is this one. So we have E2. Okay, let's calculate delta 2. So delta 2 is E2, and now the derivative of the activation with respect to Z. But the derivative of the activation with respect to Z, we said it is Y times 1 minus Y. So we have this thing, so we have now minus 0.088. Okay, so now we have delta 2. Very good. Now let's compute E1 and delta 1. So E1 is this one, but this one is delta 2. So this is delta 2 times this derivative. And this derivative is the derivative of the combination here with respect to the activation in the previous layer. So, but there is just one weight there, that is this W to 1. So it will be W to 1 times the input to that layer. Okay, so we have it there, and it is this one. Okay, delta 1. So delta 1 will be this one, but this one was E1. So all this is E1. We have already calculated. And now the derivative of the activation here with respect to the combination. It is ReLU. And ReLU is identity. So it will be just 1. That is the input. Very good. So then now we have E1 delta 1. So let's collect them there. And now we have to compute the derivatives with respect to the weights. Okay, so the derivative with respect to the weights, it is, this one is delta 2, and then the derivative of the combination with respect to the weight. But the derivative of this with respect to the weight, it is x1. Okay, so it is delta 2 times x1. And x1 we had here, it was 0.5, so it is this derivative. And the same for the others. So it is delta 1 times x1 and delta 1 times x2. And then we simply have to substitute what are the values, this x1, x2. So we substitute, we have these ones. Okay, so now we have all the derivative of the cost with respect to all the weights. And here we have them. And now we update the weights. So here I'm a little bit abusing the notation. This is kind of programming notation. So it is the current weight minus the gradient. And the gradient, let's say that my learning rate is 0.1. So it will be, we have all the derivatives here. So it will be 0.1 times the derivative, 0.1 times the derivative, and so on. And then these are the new weights. So the previous weights, they were, this was 1, now it will be 1.0044. The other one, this one was 0.5, and 0.5044. So it changes a little bit. And this one doesn't change. And it is interesting. Actually, I did a mistake. There should be a minus here. So this should be minus 0.5. And the reason why it doesn't change is because the input is 0. And if the input is 0, this weight has not been used to compute the output. So I don't know how to change the weight so that the output is better, because it has not been used. So it makes a lot of sense that we don't change that weight. And so now we have new weights. So we have new weights. This one stays, and then you compute forward, and the new output is 0.624. Before it was 62.2. So our goal of getting a little bit closer to the output, to the desired output, has been fulfilled. And now you would iterate again and again and again with many more data, and so on. Okay? So we have tracked for just one of them. Very good. Let's say that my learning rate is now 100. So if my learning rate is 100, these are the new weights. These are the new weights. And if you compute the output for the new weights, then the output is 1. So you are exactly at the desired output. So that gives you an idea that this learning rate controls how fast you will go towards the target. So here with 0.1, we are moving just a little bit, and you will need many iterations to get to the desired output. Now you do it very in just one step, you go directly to there. The problem with this is that it is very unstable. You know that this learning rate, it is making big jumps in the landscape of the goal function. So it can result in very unstable weight updates. And actually, this one goes to the right place, but not because the weights are regular, but because the output, the last activation function saturates. Then it doesn't matter if you are very far. Your output will always be 1. But it is not good to go so quickly to the minimum or to the right answer, because these updates are very stable. You could have very weird waves. Okay, any question here? No? Okay, so that's all for today.